Okay. Are there any other questions? All right. So chemical bonding, chapter 10. As I mentioned, you can use the valence electrons to predict how atoms bond together in 3D space, and they form these big shapes. One of those structures that's important for, any living thing really, are proteins. You can zoom in on this. So this is a protein. The sort of like hazy, blobby bit on the outside here is like the electron density around it. This ribbon is the actual structure of the molecules, sort of flattened out and simplified because these are massive, massive molecules. I mean, if, like the heaviest thing on here is like 222, 262. The atomic mass of these things is like 3,000. And it's all made up of carbon, nitrogen, oxygen, smaller atoms. But one of the critical things about these structures is that their shape determines their activity. So if we can develop molecules, in this case it was an HIV drug, if we can develop a molecule that somehow fits into that structure and makes it stop working, then we can stop HIV, a virus, from reproducing. Or we can stop different diseases from occurring. Now the hard part is that those structures are incredibly complex. So while it's easy to predict the shape of a small molecule, when you add thousands of atoms together, it's very hard to predict. So this is that representation of that HIV enzyme. And then the inhibitor actually fitting right here in the middle. So it's pretty powerful theory. So our bonding theories predict how atoms bond together to form molecules. Right, so bonding theories form molecules. We can predict what combinations of atoms form compounds, which we've covered a little bit with nomenclature. And we can also predict what combinations do not form compounds. At the very basic level, this has to do with those valence electrons. And then later in the chapter, we'll get to how these bonding theories can explain the shapes and how the shape then affects chemical properties. The method that we're going to focus on for doing all of this is Lewis theory. So it's a simple method for making quick, everyday predictions about molecules, especially useful for smaller molecules. So in Lewis theory, the valence electrons of main group elements are represented as dots surrounding the symbol of the element. So that's what we looked at last week in lab. I gave you a few examples of that. We looked at the Lewis dot worksheet. Those are called Lewis structures or dot structures because it's the symbol with a bunch of dots. The number of valence electrons for any main group element, except for helium, is equal to the group number of the element. So that is on these periodic tables, right, 1 and 2, and then we skip over to 13, 14, 15, 16, 17, and 18. And those are 3A, 4A, 5A, 6A, 7A, 8A. And that's how many valence electrons they have. So if we wanted to pick out, let's say, boron, how many valence electrons does boron have? How many valence electrons? 5 total electrons, yes. 3. So it's in column what would be 3A, but on this one it's 13. Same thing. So it has 3 valence electrons. So our Lewis structure of boron, move it over a little, we'll just put 3 dots around boron. So do the electron, we do oxygen the same way, but let's write out the electron configuration first. So for oxygen, what's the first orbital? Yeah, 1s, and then with 2 electrons would be 1s2. And then we move to second row, so 2s2. And so that's the S block, which are the groups 1 and 2. And then we move over to the P block, where oxygen is the 4th element into the P block. All right, so boron, carbon, nitrogen, oxygen. So that's 2p4. And again, looking at the electron configuration, so we could use the periodic table to figure out how many valence electrons there are. We can also use the electron configuration, where we just look at the highest principal quantum shell. So that's the number here in front of the 2 and the P, or sorry, the S and the P. So 2 is our highest principal quantum shell. We add up those exponents. So oxygen has 6 valence electrons. So our Lewis structure for oxygen, let's write an O for oxygen, the symbol. And then one at a time, we place these electrons around it. So 1, 2, 3, 4, 5, 6. So we are Lewis structure. So each dot in the Lewis structure, actually let me draw out oxygen here so we have it as a reference. So 1, 2, 3, 4, 5, 6. Each of those dots represents one of its valence electrons. I'm going to place the dots around the element symbol with a maximum of 2 per side. So you kind of think of oxygen as being inside of a box. And so all of these go on one of the sides. Two per side at most. So it doesn't matter where those dots are arranged. So this is correct, and then this minus the box would also be correct. So here I put 2 electrons here and 2 electrons here. And here I put 2 on top and 2 on the right side. So it doesn't matter how those are arranged necessarily, just that you have the right number and that there's only 2 per side. And we fill them in one at a time. And that's related to, if we think of the orbital diagram. If you remember orbital diagrams, when we fill in all of oxygen's electrons, we do so for every level and every orbital one at a time. So 1s, you put 1 and then a second one in there because there's only one orbital to fill. But when we get to P, we would go 1, 2, 3, and 4. So don't pair them up until we have to. And you could ignore the stuff about mastering chemistry. And we mentioned this too when we talked in chapter 9 about valence electrons, that everything wants to have a stable configuration, which is 8 valence electrons. So it's any configuration that's the same as the noble gases. Okay, so just switch this to black. What would our Lewis structure for helium or for hydrogen be? Just 1 dot. And then for helium? 2. 2. Helium has 2 valence electrons. And then for lithium, how many dots? Just 1, because now we've moved to a new principal quantum shell. So every time we move down a row, we start over with the number of valence electrons. So beryllium would then be 2, and then boron is 3, carbon is 4, nitrogen would be 5. That's the first one where we double up. Oxygen is 6, fluorine is 7. Neon, oh, I guess I should do this in the correct order. Neon is 8. So aside from hydrogen and helium, everything else wants 8 electrons, because that's a full valence shell. For hydrogen and helium, they're just trying to get to 2. So in Lewis theory, which which we're going to use to predict these chemical bonds, involves the sharing or transfer of electrons to attain stable electron configurations for bonding atoms. This is where we're going to call back to way back to chapter 5. So in chapter 5, we named compounds. We had ionic compounds. Ionic compounds have ionic bonds. So in these ionic bonds, it's a transfer of electrons. So electrons are fully moved from one atom to the other. And it's always from the metal to the nonmetal. Our molecular compounds have covalent bonds where the electrons are shared. So instead of fully giving up any electrons, they say we're going to use these two electrons together in a bond. So the octet rule, which is going to guide how we place these electrons and move things around to make stable bonds and to make sure, is to make sure that everything has an octet, or 8 electrons. And then the exceptions, of course, are hydrogen, also lithium and beryllium. Because again, lithium and beryllium will lose 1 and 2 electrons respectively to have the same electron configuration as helium. And then there are 2 other exceptions, which is boron and aluminum. Sometimes they only have 6 valence electrons. Which we went over those examples on the Lewis dot structure, or the Lewis dot worksheet. Okay, so we've got ionic bonds where we transfer electrons, covalent bonds where we are sharing electrons. Actually, so these ionic bonds is going to be a metal plus nonmetal. And this is nonmetal plus nonmetal. So covalent bonds are between 2 nonmetals. Ionic bonds are between a metal and a nonmetal. Okay. So let's write Lewis structures for magnesium and sulfur. How many valence electrons does magnesium have? 2. So it gets 1, 2 electrons. And then how many does sulfur have? 6. So 1, 2, 3, 4, 5, 6. What's the next slide here again? Yeah. So notice that if sulfur wants to get to an octet, it needs 2 more electrons. Because it has 6 valence electrons, 2 more would get it to 8. Magnesium, which is on the left side of the periodic table, wants to lose 2 electrons so that it can have the same electron configuration as neon. So it wants to open up that lower shell, whereas sulfur wants to fill up its outer shell. And also, go back to this one again, sorry. It's a metal and a nonmetal, so this is going to be an ionic bond. So we have metals bond with nonmetals. We transfer those electrons because magnesium wants to get rid of them. Sulfur is looking to get more. So the metal becomes a cation because now it has more protons than it has electrons, so it has an overall positive charge. For sulfur, or a nonmetal, it becomes an anion because gaining electrons means it has more electrons than it has protons, so it has an overall negative charge. And that the attraction then between the cation and the anion is not because of the shared electrons or the transferred electrons necessarily, it's because they have opposite charges. So it's like opposite ends of a magnet sticking together. So we represent this magnesium, and I'm going to put these over here, sulfur, So we can transfer these electrons over to sulfur. And then we would have Mgd plus and S with 8 valence electrons, 2 minus. So this is also why when we're naming ionic compounds, we have to make sure that these charges balance. Because if the charges don't balance and equal 0, that means that one or the other of these has too many or too few electrons to get to an octet. Okay, so for potassium and chlorine, how many electrons does potassium have? Just 1. Valence electrons, I should say. And then chlorine has 7. So we're going to transfer this 1 electron from potassium to chlorine. And then we'll have K plus and Cl, all of its electrons are minus. And actually, we're going to get to this in a second, but to help keep that negative charge separate from the dots or getting confused with anything else, usually put brackets around the anion and then the charge outside of those brackets. So when we transfer that electron, chloride ion has an octet. Now it's balanced. And potassium loses its only valence electron, so it reveals the octet underneath from the previous shell, which, because there's no higher energy electrons, is now its valence shell. So the Lewis structure of an anion, again, I just mentioned this, is written with brackets. So it would be potassium just like that. All right, so let's try sodium bromide. And again, how many electrons does sodium have? Just 1. And then bromine has 7. So again, we're going to transfer that electron. And because sodium lost 1 electron, it's now got a positive charge. And because bromine gains 1 electron, now has a negative charge. Cool. Pretty simple so far. Now, so far we've done magnesium sulfide, which magnesium wants to lose 2, sulfur wants to gain 2. It's an easy exchange, 1 to 1. Same for sodium bromide and potassium chloride. Those are both 1 to 1. But the Lewis structures also predict why we form other ratios. So if we have barium, how many electrons does barium have? 2 valence electrons. And then fluorine each has 7 valence electrons. So for barium to be able to give up 2 electrons, it needs to share 1 electron each with a fluorine. If that's the only thing it's got around to share with, or transfer its electrons to, it needs to react with 2 of those. So then we would have fluorine with all 7, or sorry, with all 8. Barium with a 2+, and then another fluorine fluoride now, the minus. I believe this would actually be written as it's an alternate way you could write this out. All right, so we say we've got 2 fluorines, each with 1 minus. So it can get a little bit more complicated even. But it's not too tricky. So if we have magnesium and nitrogen. So magnesium has 2 electrons, 2 valence electrons. How many valence electrons does nitrogen have? Somebody say it? I thought I heard it. 5, yeah, thank you. 5 valence electrons. So how do we combine magnesium and nitrogen so that we've got nitrogens, you can have more than one, nitrogens that have accepted enough electrons and magnesiums that have been able to give all of theirs up. What was that? We can add another magnesium. Okay. So now we've got 4 electrons that we can give away. And how many does nitrogen want? 3, because it has 5, so it wants 3. So now we've got too many electrons on magnesiums. So we're going to add another nitrogen. Oops. Again, going to have 5. So now we're short again on this side, because 3 of these, I can draw these in, 3 of these will go over here. Then 1 goes here. So we're going to add now just 1 more magnesium. So that one goes here, and that one goes there. So we'll actually have 3 Mg2 plus and 2 N3 minus. The other way you can look at a problem like this is the same way that we would decide how many magnesiums and nitrogens would go together if we were going from a name, magnesium nitride, to the formula. So we know magnesium only forms one type of charge, which is a 2 plus, and nitrogen only forms one type of charge, which is a 3 minus. So essentially what we've done here is just the crisscross, right? The 3 goes here and the 2 goes here. Mg3 and 2. So the ratio between those comes about because that's the right ratio, or the smallest ratio, for transferring all of the 3 magnesium's electrons to 2 nitrogens so that everything has an octet. Still good? No questions? All right. So for the ionic compounds, it's basically the same way that you would, ends up working out the same way that you would write the formula from the name. Right? The charges line up because that's how many electrons are transferred. For molecular compounds, it gets a little bit more complicated, but we've got some rules that you can follow that should get you to the right answer every time. Because in molecular compounds, we have covalent bonds where the electrons are shared. So the ionic compounds, it was magnesium giving up all those valence electrons to nitrogen, or sodium giving them up to chlorine. But in molecular compounds, they're sharing those electrons instead. So they share those to attain octets. So if we write out a Lewis structure for hydrogen, right, so it's hydrogen and then 1 electron. Remember, hydrogen only needs a duet, so it only needs 2 electrons. So if we add another hydrogen with 1 electron, they can each share their 1 electron in the form of a bond, And now because those electrons are shared, they both have a duet. Oh, okay. I guess I got a little ahead of myself. Also, if we draw out the Lewis structure for oxygen, oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, 6. You can also take 2 hydrogens here, because oxygen has 6 electrons, so it wants 2 more. But hydrogen's also looking to get another electron. So they can share their electrons, and we'll get oxygen with bonds to 2 hydrogens, which is why water is H2O. Those bonds mean that oxygen gets to have an octet, because we can count these. These bonds are made up of 2 electrons. So oxygen has 2, 4, 6, 8 electrons. And then each of the hydrogens just has the 1 bond, and that's all they need, so they have their duet. So if we draw out oxygen, or this water again, we can move these things around. So still water, still has the same number of hydrogens, oxygens, bonds, just writing it a little differently. Our bonding pairs are the electrons and bonds. Right, so it's a bonding pair of electrons. And then lone pairs are these non-bonded electrons. So every line, every bond counts as 2 electrons, and every lone pair counts as 2 electrons. So you will see in some places bonds written out as just like 2 electrons between hydrogen and oxygen, something like that. It's a little less clean. We're going to write them out as lines. So Lewis theory also explains why the halogens form diatomic molecules, and not just the halogens. It showed you how hydrogen with 2 hydrogens with 1 electron each can share those and form a diatomic element or diatomic molecule. But we could also do for bromine basically the same thing. So each bromine has 7 electrons. 7 there, 7 there. So if they each just share 1 electron between the 2 of them, or each contribute 1 electron to share. You can have bromine with a bond to bromine. And now they each get an octet. And this is why bromine, iodine, nitrogen, we'll get to nitrogen, chlorine, hydrogen, oxygen, and fluorine all form diatomic molecules, although some of them do it a little bit differently. So bromines with just a single bond, fluorine, chlorine, bromine, and iodine can all share just 1 electron with another element or another atom of the same type and have full octets. If we look at oxygen, though, we have 6 electrons. So 1, 2, 3, 4, 5, 6. So we can share, let's just move this over. We share 1 electron between the 2 of them, form 1 bond. That means they still have 5 electrons that aren't bonded. Now oxygen, each of these oxygens has 2, 4, 6, 7 electrons. So we can share 1 more electron from each. and then that will give us oxygen with a double bond and 2 lone pairs. So oxygen exists as a diatomic molecule because it can share 2 pairs of electrons. So the double bond, right, we're sharing 2 pairs of electrons. That actually makes it shorter than a single bond, and it makes it stronger than a single bond. So the distance for a double bond is about 121 picometers, which I believe is times 10 to the negative 12. 1 times 10 to the negative 12 meters. And then a single bond is 148 picometers. So when you create this second bond, it brings those atoms, the nuclei, a little bit closer. So if we look at nitrogen, nitrogen has 5 valence electrons. So what do you think we're going to have to do with nitrogen? It's going to have a triple bond because each of these has 5, so they need to be sharing 3 electrons each. So each of these bonds is still 2 electrons. So that's 6 electrons in the triple bond, and then 2 lone pairs. So when we count these electrons, we have 2, 4, 6, and 8. And for the other nitrogen, it's 2, 4, 6, and 8. Bonds are counted for both of the atoms sharing that bond. So if a double bond's shorter than a single bond, a triple bond is even shorter. So when you share 3 pairs of electrons, you get an even stronger bond. And that also makes it a shorter bond. So it goes down to about 110 picometers, whereas the double bond was 124, and then 141 for a single bond. This makes nitrogen very inert, doesn't react with anything because nothing can really break, or not many things can break that bond. This actually ended up being this is sort of like the root of the problem for why crop rotations were a big thing. Growing tobacco, this is going way back. Growing tobacco is a super nitrogen depleting plant. And so farmers would growing tobacco, depleting the nitrogen, and then getting really, really bad crops after that. So that's where, I don't remember what his name is, some guy came along and was like, hey, plant peanuts. Because the only way they knew at the time to put nitrogen back into the soil in a form that plants could use was the bacteria that is symbiotic with the roots of peanut plants. And other plants too, other legumes. And then the Haber-Bosch process, which I think was 2 guys, was like the first chemical way to take nitrogen out of the air and split that molecule apart into fertilizer. So nitrogen's pretty cool. All right. So what if things get more complicated than just these diatomics? We've got a set of steps, and we actually went over some of these steps before last week in lab, but we get a refresher now and sort of a formal listing of those rules. So the first step is to write the correct skeletal structure of the molecule. So you're going to take all the atoms, you're going to write them out in their relative positions. And there are some caveats to this. So hydrogen atoms are always terminal atoms. So they're never going to have more than 1 bond because they don't have more than 1 electron to share. So they're always going to be at the end of molecules. The other thing is that many molecules tend to be symmetrical. So if you get a lot of different things going on, especially on the Lewis dot worksheet, make sure you try and place those as symmetrically as possible. So one of the examples, I think was I think this one's on there, C2F6. Let's do C2H6. So in this case, we have 2 carbon atoms and 6 hydrogen atoms. So our skeletal structure, we know that hydrogen can't be in the middle anywhere because it can only form one bond. And now we want to place these 6 hydrogens evenly around the 2 carbons. So there's going to be 3 around one of the carbons and 3 around the other. And then the next step would be to draw in bonds. So hydrogens will always be terminal positions, and carbons, actually, this is another rule that's not on here. Carbon always has 4 bonds. Oh, I guess we do cyanide where it doesn't have 4 bonds. Carbon almost. And when I say bonds, that includes things like triple bonds, or triple bonds would be counted as 3. So if you had C2H2, then you would have H, C, you would have 3 bonds, C and H. So each of those carbons has 4 bonds. Right, so there's 3 here and then 1 there. So the second step for any Lewis structure, and I would argue that the second and third steps could be interchangeable, but the second step here is to write or to calculate the number of valence electrons you have for your molecule. So the sum of, or the adding together, the valence electrons of each of the atoms participating in that molecule. And again, we can get the number from the periodic table pretty easily. And then for ions, so if you have something like NO3 minus nitrate, this negative charge would add an additional electron. Or if you had NH3 plus, you would subtract 1 electron from your total valence electron pool. So let's just calculate this for nitrate. We have nitrogen and oxygen. So there's 1 nitrogen, 3 oxygens. Oxygen has 6 valence electrons, and nitrogen has 5. So we'll get 5 and 18. And then because we have that negative charge, we would say we're going to add 1 more electron in. For ammonia, we have nitrogen, hydrogen, and this is 1 of those, and 3 of these. So hydrogen only has 1 electron each. Nitrogen has 5. So that'll give us 5, 3 electrons. So we'd add these together to get 8 electrons. Then we would subtract 1 electron because we have a positive charge. So our total here would be 7 electrons. Okay. So after you've done that, wait, do we skip the bonds? Oh, I guess, oh, weird. Yeah, I kind of skipped the step of adding in the bonds. Or I guess that's what this is. So begin by placing 2 electrons between each pair of atoms, which would be the minimum number of bonding electrons. I was thinking of that as a step all its own. And then you want to distribute the remaining electrons first to terminal atoms, and then to the central atom, giving octets to as many atoms as possible. Let me pull this example again. So I'll do it this way. If we have C2H6, we have our skeletal structure, and we have calculated that we have 10 valence electrons. The first thing we want to do is place these bonds. Actually, sorry, let me change this up a little bit, because this is not really going to illustrate my point. Okay, sorry, C2H4. Also calculated the wrong number of electrons. C2, that's 8, plus another 4. Sorry, it's 12. All right, so we have 12 electrons to place. We start by putting in these bonds. It's the minimum number of bonds. And then if you remember, we'll subtract those out from our total here. So we placed 1, 2, 3, 4, 5 bonds. And so we multiply that by 2 because each of those has 2 electrons. So we've got 10 bonding electrons, which leaves us with 2 electrons left. So the point I wanted to make here is that we distribute these first to terminal atoms, but only if they need more electrons. All right, so hydrogen only needs 1 bond, and then it's got a duet. So we're not going to add any extra electrons to those. They've already got their octets, so these 2 electrons instead will go to one of the central atoms. So first to terminal atoms if they need more electrons, and then to the central atom, giving octets or duets, when appropriate, to as many atoms as possible. So of course that last structure wouldn't be complete, because this last step here, let me make sure it's the last step, yep, is to make sure that everything has an octet. So if we look at this carbon on the left, it's got 2, 4, 6, 8, so that has an octet. But this other carbon has 2, 4, 6. So now we take this lone pair, and you'll do this in general for any lone pair that's attached to something that doesn't have enough electrons, and we'll use that to form a double bond. So we'll get carbon, double bond carbon, and now everything has an octet, so we can stop there. All right, so for carbon monoxide, so our first step is to draw out the skeletal structure. So you have carbon and oxygen. That one's easy. We don't have to worry about what's the central atom because we only have 2. Oh yeah, actually let me do it this way. So this is our skeletal structure. And then we want to calculate the number of valence electrons. So how many valence electrons does carbon have? 4. And then oxygen has 6. So we have a total of 10 valence electrons. So we're going to place 1 bond between carbon and oxygen as our minimum number of bonds. And then we'll have our total 10 electrons minus the 2 bonding electrons. So we'll have 8 electrons left over. So go this way, and then we're going to go this way. So now we can place those electrons in pairs around these atoms. So we've got 8 to place, so we'll go 2, 4, 6, 8. Whoops, that's 10. Okay, so we placed our 8 electrons. Now we can see that these have 2, 4, 6 electrons for carbon, and 2, 4, 6 electrons for oxygen. So we'll move one of these lone pairs from here into the center. You'd use either one. So we get a double bond. So now carbon's good, but oxygen is not. So we'll take another lone pair now from carbon and add that as another bond. So we draw this. So now carbon has 2, 4, 6, 8. And then oxygen also has 2, 4, 6, 8. So we're good. That's the Lewis structure. Any questions? Oh, that's when we placed this. So we went from here with no bonds at all. We placed those bonding electrons there. Any other questions? All right. More examples. So now we've got an example of one with multiple atoms going on. We need to decide what's going to be the central atom. Usually that's carbon. If carbon's involved, it's almost always carbon. The other thing we know is that hydrogen can't be a terminal atom. So, not that yet. So we're going to need carbon, oxygen. Then we're going to put both of these around carbon. Okay. I was trying to come up with another justification other than just because. Carbon almost always, this is a little bit into organic chemistry, carbon almost always has 4 bonds. Oxygen almost always has just 2 bonds. And then hydrogen always has 1. But I also can't think of a reason that this wouldn't be wrong necessarily. Yeah, this is the correct way. Just know that, yeah, if you have carbon and other atoms, carbon's the central one. Okay, so we have our skeletal structure. What's our next step? Valence electrons. Yeah, we want to know how many total valence electrons we have to work with. So we have hydrogen, carbon, oxygen. So hydrogens, we have 2, 1, and 1. You can do this in whatever way works for you. If you can just look at them and add them up, you can do that. Or if you want to write them out like this, that works too. So each of the hydrogens, we have 2 hydrogens, so it has 1 electron each. And then carbon has 4 valence electrons, and oxygen has 6. So that'll give us 2, 4, and 6. So for a total of 12 valence electrons. And what's the next step? Yeah. Our minimum number of bonds, like that. Huh? 6 bonding electrons. So we'll subtract our 6 bonding electrons from our total valence pool. and that'll leave us with just 6 electrons left over. So here's where we have now terminal atoms and a central atom. So we want to place all of our electrons around the terminal atom first, terminal atoms. But in this case, hydrogen and, well, both of the hydrogens don't need any more electrons. So we're not going to give them any more. Instead, we'll place those 2, 4, 6 around oxygen. If we had more electrons, we would also place those, we would then go from the terminal atom, once it's full, to the central atom. But here we ran out. So our next step is to count and make sure we have octets. So for carbon, it's got 2, 4, and 6. Oxygen's good, 2, 4, 6, and 8. So oxygen can share one of its lone pairs with carbon. And so we'll get a double bond between oxygen and carbon, giving everything an octet if it needs it, or a duet for the hydrogens. All right. So for polyatomic ions, we follow the same procedure. It's all the same stuff. We've just added the fact that there's a charge now associated with that ion. So like I mentioned earlier, we add 1 electron for negative charge, or we subtract 1 electron for each positive charge. So if we have something like phosphate, which is PO4 3 minus, we would add 3 more electrons for that. I don't think we actually have a positively charged an ion, a polyatomic ion with more than 1 positive charge. But if it was like 3 plus, you would subtract 3 electrons from your valence pool. So then when you get to the final structure, you would put brackets around it and then add that ion. So, insert phosphate Lewis structure here. Can't just do those on the fly. All right, for cyanide though, what's our first step? Skeletal structure. So we have our skeletal structure, and then we get our valence electrons. So actually I will write this out because, so for carbon, we only have 1 carbon, 1 nitrogen. Carbon has 4 electrons, nitrogen has 5. And then we also have a negative charge. So because we have a negative charge, we add 1 more electron. So we'll have 10 total valence electrons. And then we'll put in our minimum number of bonds. So it's 2 electrons that we'll subtract. And then we can start adding these electrons as lone pairs. So we have 8, so 2, 4, 6, 8. So are we done? Not yet. Now we can start sharing lone pairs because each of these has 2, 4, 6. So if carbon shares 1 lone pair, it'll still only have 6. So we'll also have to share a lone pair from nitrogen. So we get carbon, triple bond, nitrogen. You can also go one at a time and then recount and then share another one and then recount. You can't have more than a triple bond. So then our last step, because this is an ion, is to put this whole thing in brackets and give it that negative charge. Because the overall charge of the ion is -1. 1 minus. Still good? Let's follow some steps. All right, so for hypochlorite, start again with our skeletal structure. And then we want to count these electrons. So how many does chlorine have? 7. And then oxygen? 6. Yep. And then we'll add one more electron because we have a negative charge again. It's easy to forget, but it is important. So now that gives us 14. So now we can place our minimum number of bonds, which is 1, and subtract those 2 electrons from our valence pool. And then go about distributing these electrons. 2, 4, 6, 8, 10, 12. No double bonds necessary. And then the last step here is to brackets and the negative charge. All right. Yes, sometimes there are exceptions to the octet rule. The ones that are on the Lewis dot worksheet are boron, which will just have 6 electrons, and aluminum's the other one. If you notice, boron and aluminum are in the same column, so that's why they do that, or why they're both like that. But in those situations, you just write the best Lewis structure possible. Yeah, especially when there's an odd number. So this is why, actually if we go back a little bit, anything with nitrogen is going to have some charge on it, whether it's a positive one or a negative one, because we have to add or remove 1 electron, because nitrogen has 5. Okay. There are also things called expanded octets. I don't think there's any of these. Oh no, there's a whole section of these on the Lewis dot worksheet. But in that case, what you do is you place them all around the central atom. So these, you know, it's a central atom because there's only 1 sulfur and 6 fluorines, or 1 phosphorus and 5 chlorines. So the single one goes in the center. Those are expanded octets. You won't have expanded octets for anything in the second row. Things like phosphorus and sulfur and below can have expanded octets. Okay. So there are some situations too where there's more than one good Lewis structure. So if we look at sulfur dioxide, we have sulfur will be in the middle, it's our single atom, and the oxygen's around it because that makes it symmetrical. Otherwise it wouldn't be symmetrical. Let's do this one quickly. So we have 18 total electrons, 18 total valence electrons, and I've just placed 2. That's a minimum number of bonds. So then we'll have 14 valence electrons left to place. Actually, let me move this to the center. So I'll start placing those around the terminal atoms first. 2, 4, 6, 8, 10, 12, 14. So once the terminal atoms are filled, then you do the middle one. And then sulfur still only has 6 electrons. 2, 4, 6. So which oxygen should we take a lone pair from and make a double bond? The correct one, the right one. Either one. So this is, yeah, sorry. No, that's fine, because the right one is correct, but the left one's also correct. That's the point. So if we do the right one, we'll do the right one first. Then we'll end up with this structure. Everything has an octet. Let me do this in a different color. But we can also do the left one. And everything also has an octet. These are called resonance structures, and they're both correct. But in reality, it's more of a hybrid between the two. So it's not the double bond on one or the double bond on the other necessarily. So both of them predict that it would have 2 separate kinds of bonds. In reality, like breeding dogs, you end up with a hybrid between a double and a single bond. So it's like a bond and a half. So if you look at those 2 bonds, they're actually intermediate in strength and length between a double bond and a single bond. So it's halfway between the length and halfway between the strength as well. I believe there are resonance structures on the Lewis dot worksheet. You just write one of them. So here's that sulfur again. So both of these are correct. And when you're writing out correct Lewis structures, you can draw an arrow between them. So it's this one or this one. But it's actually something in the middle. All right, this will be the last. Yeah, this is the last one. All right, so first step, skeletal structure. Back to this. I don't know why. Okay, so in the middle here. Nitrogen and our oxygens. How many electrons does nitrogen have? 5. And oxygen? Yep. So we have 2 oxygens, so that's 12. And then we have a negative charge again. So we're going to add 1 more electron for that. So that'll make our total here 18. And then we can place our minimum number of bonds. So that's 2 bonds, so 4 electrons. Looking very similar to sulfur dioxide. So if we go and place these electrons now, 2, 4, 6, 8, 10, 12, 14. And again, our central atom, nitrogen, doesn't have enough electrons. So there's 2 resonance structures we can draw. We can take from the right one, and again we'll have nitrogen, double bond, oxygen. Let me do it this way. Or we can do 1 lone pair from this side. these would both have brackets and charges. For resonance structures, if it asks for both, that's how you do it. Any other questions? Okay. Next time we'll get into predicting the shapes.